Good day once again, grade 12s, and welcome back to another video on the anti-science theory. So in this video, we're going to be continuing from the very first video, which was on the introduction to vertical projectile motion. Once again, if you have not seen that video, I will drop the link to that video in the comments in the description below. But today I just wanted to look at the diagrammatic representations of rather interpretations under VPM. Please make sure that you like, comment, share, and subscribe. Make sure that you share these videos with your friends, your families, even your baby brothers who are 12. They will also need this in a couple of more years. But for now, the focus is on you and making sure that you get into that distinction with you get into that exam room with full confidence and attaining your distinction, which is very easy to attain if you could just give it your all. Make sure that you understand everything. Make sure that you give yourself time to rest, time to study. Right? You can't just study all the time. Your body also needs to rest. Your mind also needs to relax, to calm down, to chill, so that from there it can be at full force. And when you study effectively, ensuring that you get yourself those good results at the end of the year. But nonetheless, I think it's best if we just get into the video. Right, so I just want us to have a little diagram here on the side, which is a diagram that most examiners will use when you're looking at questions under vertical projectile motion. So for starters, I'm going to start by saying, okay, so I'm going to have a certain building here, right? So I'm going to have my building here. I'm not really good at drawing. So, right. So let's say, and on this building has a certain height, right? An unknown height. We'll call that height H. Right, so since the building has an unknown height H, what happens? So this building is from the ground, which is this point here. So that is from the ground, okay? The ground, cool. So this is the ground. Okay, so what happens? So let's assume that I have a ball here. Let's call that ball. So we're gonna call this ball, right? So here's ball. So what happens? So what happens is that after some time, rather not really after some time, but what happens initially is that this ball is thrown upwards, right? So look at something. This ball goes up and then it eventually comes back down. Right. So remember, everything that goes up must come back down. So this ball goes upwards, right? And then as it goes upwards, right, it gets to a point here, right? And then it continues to go up. And then there's another point here, which is right there. And then it hits the ground, right? So I'm going to call this point where it started, I'm going to call it point A, right? The point above the roof. And then I'm going to call this point here point B. And I'm going to call this point here C. And that point there point D. Right. So what I want us to understand real quickly is everything I'm about to explain right now, I'm going to try to explain it in the best way possible, right? Cool. So what I'm going to do is that I'm going to take this portion here, right? I'm going to take this portion here and I'm going to write it on the side. So this is what I'm going to do. So I'm going to write it right there. So I'm going to have something like that. Then I'm going to have something like that, right? So remember that we had our point here, which was point A. We had our point there, which was point B. And we had our point there, which was point C. Okay? Right. So I want us to focus on something real quick before we go back to our building diagram. So what I want you to note here is that when I have this certain diagram, we're going to be focusing on the diagram on the right-hand side, this hemisphere diagram. So what I want you to notice is that at point A was the point where the ball was released, right? Though this is the point where our ball was released, or rather the ball was thrown, not released, but thrown. So this ball was thrown vertically upwards, right? So it was thrown vertically upwards at a certain velocity. So that velocity is unknown, right? So it's an unknown velocity. Right, and then this ball goes up, goes up, goes up, like that. So it goes up, goes up, goes up, and goes up, and then it eventually comes down. Right. So the very important point that you must understand here, besides the fact that everything that goes up must come down, is the fact that when my ball goes up, something happens to the ball. Now, what is it? Every time my ball goes up, remember, what did we say when we spoke about the introduction of VPM? We said that the only force acting on the object is gravitational force. That is, every time my ball goes up, Fg pulls the ball down. So gravitational force pulls the ball down, right? So that's the first point you must know. And as it goes up, so this is during the upward motion, right? So this is during the upward motion. Just to be very precise and very simple. So during the upward motion, Fg pulls the ball downwards, right? What also happens? The velocity of the ball decreases. That's a very important point. The initial velocity of the ball decreases. Okay? So that's very important. That is, say that my ball started, okay, I'll get to that point. Right, so let me just write this as not upward motion only, but let me just be specific as I used with my letters. So at this portion here, from A to B, the ball moves upwards, right? That's from point A to point B. The ball moves upwards. As the ball is moving upwards, gravitational force pulls it down, and the velocity initial decreases, right? So what exactly happens at point B? So at point B, this is what happens. So we have the point A to B, and we have point B. At point B, this is what we say. At point B, we say that the velocity final is 0 meters per second, and that's the velocity at point B. Why is that? Before I get to the velocity final point, we call point B, guys, I'm so sorry, please try to journey with me. We say that point B is known as our maximum height. So point B is our maximum height, right? And at the maximum height, the velocity of the ball, which we will call the final velocity, is equal to 0 meters per second, right? Those are the things that I want you guys to make sure you understand. Right. So once again, from the point A to B, what happens? The ball moves upwards, right? And as it moves upwards, what happens? Let me quickly just get my highlighter. As it moves upwards, we notice that gravitational force pulls the ball down, right? And as that happens, what does that result in? When gravitational force pulls the ball downwards, the velocity of the ball ends up decreasing, right? And what happens at point B? Now, when we get to point B, we say that is the point that is referred to as the maximum height. At the maximum height, what do we say? We say that at the maximum height, the final velocity of the ball is 0, right? That also means that the ball is momentarily at rest. The reason I say momentarily, guys, is because it doesn't just stay there forever. It must come down. So for that particular period of time, it becomes stationary. So it is momentarily at rest, right? Momentarily at rest. before it eventually comes down, right? So when does it come down? So that is when we focus on these points, the final points, that is from B to C. That's when the ball goes down, right? So from B to C, that's when the ball goes down. So what happens during those parts? From B to C, our ball is going to be going down. What happens when that happens? Remember, nothing changes. Gravitational force still pulls the ball downwards, still pulls the particular ball down. Why? Right? And what happens? As that happens, I want you to think about it. Think about, let's say you are pulling on a rope. Let's say you have two friends of yours, and let's say you have three friends, two on one side, two on the other side, right? So that's you included. And you guys are playing tug of war, right? So remember tug of war. I'm not sure if we all know the game tug of war, where you pull on a rope, right? It's basically a game that tests one's strength. So tug of war is a game where the rope is being pulled on one side and being pulled in an opposite direction on the other side. So what happens is that when you cross a certain line, then the ones that have crossed the line basically have lost, right? But that's besides the point. The point is, I want you to understand, just imagine it. Imagine you pulling a rope that was initially hard to pull, right? Think about it. When you're pulling a rope that is initially hard to pull, why is it that rope is hard to pull? That rope is hard to pull because of the fact that it is resisting your pull. That is, as you are pulling that rope, someone else is also pulling the rope in the opposite direction. That is, there is a resistance in your certain pull. So as you're exerting a force, remember a force is a push or pull, right? So as you are exerting a pull on that rope, it's actually harder to bring the rope towards you, right? As I'm pulling and I'm pulling, it's a bit hard for me to bring the rope towards me. Why? Because as I am pulling, there is a resistance. That means the rope is resisting my pull, right? But immediately when there is no one pulling the rope, it's easier for me to now pull the rope towards myself. That is, at that point, what happens? When there is no one pulling the rope, when there is no resistance, then the rope comes to me very easily. That means I can pull the rope, and as I am pulling the rope, the velocity of that rope increases. That means the rope gets pulled to me faster, right? That's very important. So when there is no resistance, that rope does what? It comes to me in a faster velocity or in a quicker speed. So that brings me back to this point. When you're moving from B to C, that is when the ball moves downwards. We say that the ball moves downwards because of the fact that FG is still pulling the ball as it was. Remember, from A to B, FG was pulling the ball, right? Sharp. And then from B to C, FG is still pulling the ball, right? So what does that mean? That means that if it's pulling the ball, the velocity, remember the tug of war, the velocity of that ball will increase in the opposite direction, in the opposite direction, in the opposite direction, right? So what am I saying? So if you look at our hemisphere once again, we have the points A, B, and C. We have said that at the point A to B, the ball is moving upwards. What does that mean? The velocity of that ball will increase. Will decrease. The velocity of that ball will decrease, and the velocity decreases because of the fact that the gravitational force pulls the ball downwards. So as the ball goes up, it is resisting the pull of gravity. And immediately at point B, the velocity of the ball becomes zero. Why? Because the ball can no longer resist the pull of gravity. And it gets to a point where it will just give up and just respect whatever gravity wants it to do. So whatever it is that gravity wants the ball to do, When it is at point B, the ball says, you know what? I can no longer resist your pull. Do with me what you want to do. And the ball then decides to come back down and follow the gravitational pull, right? That's when we get to point B to C. At point B to C, the ball moves downwards, right? That is when the ball is obeying the gravitational pull. Remember from A to B, what was happening? The ball was resisting the gravitational pull. But from B to C, the ball started to obey the gravitational pull and it then came downwards. So that is a very important point you must understand. Another point that I want to mention, right? I'm going to get to that point immediately after this. Right, I really hope that was very clear with everyone here. If you have any questions, please don't forget to type that down in the comment section. Now, I just want to get to a very important point back to my hemisphere here. Just want to take my hemisphere once again and show you something that is very important, right? So I'm going to take it here so that it can be within sight. All right. I'm going to bring my hemisphere down here. Okay. There we go. Okay, let's bring it down here. Okay, let me see. Right, let's bring it here. Where did my hemisphere go? Okay, I think there was a bit of a technical glitch right there. But anyway, right. So this is what I have. So I'm back in my hemisphere. Now I'm going to show you guys something very important. Once again, let's say I choose upwards as positive in the exam. And then I choose, or maybe I decide to choose downwards as positive, right? What happens when when I decide to choose one of these? Now, what I want you to understand is that when the ball is at equal heights, that is, check something. I'm not sure if you guys would agree with me when I say, but I really hope you do agree with me when I say point A and point C are at the same height. Point A and point C are at the same height, right? So why is that relevant? Well, for starters, when they're at the same height, we know that regardless of whether or not I choose upwards as positive, check something. When we are looking at point A to C, right? Point A to C. Okay, not A to C, let's say A and C. So I'm looking at point A and point C. At those points, we do agree that when the ball moves from A to C, why do I keep saying A and? When the ball moves from A to C, what can you say? Well, you can start by saying that delta Y is 0, right? Because it's what? The displacement. Remember, when you're displacing something, you are basically determining the change in position. That is, where was it initially and where was it final? So you say final minus initial. So if you started at a certain point and you started there, you went a certain distance and you came back to the same point, then you basically didn't go anywhere. You didn't get displaced in any particular way. So we should know that when we have the ball at the same height, our displacement is 0. Once again, if I choose downwards as positive, the same thing applies. So if I go from A to C, I should know that at that point, my displacement is once again going to be equal to 0, right? And then I go on and I say, okay, so what happens next? What you must understand is that if I'm looking at the next point, the very important point that I want you guys to understand is that if I choose upwards as positive, now I need you to be very, very attentive with this one. If I choose upwards as positive, right? Given that at point A, my initial velocity was a certain number, right? We don't know that number. Let's see. Okay. All right, so check something. So let's say at point A, my initial velocity, what is going on now? At point A, the initial velocity was let's say it was of 4 meters per second, right? Okay, so at point A, we're going to say that the initial velocity was 4 meters per second. So it was moving upwards. So notice how I have said that at point A, right, this point here, sorry, the initial velocity was 4 meters per second upwards. And I have chosen, remember, this is where I choose upwards as positive, right? So up is positive in this case, meaning anything up must also be positive. That is why I have a positive 4. What I want you to note is that when we get to point, okay, so this was point A, right? This was point A, right? When we get to point C, what happens? At point C, we'll say that is going to be our final velocity. What you must know is that at point C, the final velocity is equal to the velocity of A, but with a different sign. Meaning, at point C, I'm going to have a negative 4 meters per second down, right? Notice something. At point C, that is where the ball was moving downwards. Remember, we had our explanation right here. We said that at point from B to C, the ball was moving down. So if the ball was to continue in that downward direction, obviously the velocity would be negative, right? So this is a very important thing to consider. What am I saying? When your ball is at the same height, it shares the same velocity in a different direction. And if the direction is different, obviously that particular sign will be different as well. Once again, if I go to the downward is positive part, now check something. So if I go downwards is positive, right? I need you to look at this. When I say downwards is positive, think about it. At point A, the ball was going up. If the ball was going up, then we know that, and I choose downwards as positive. If I choose down as positive and the ball was going up, that means I then need to say the initial velocity of A must be a negative 4 meters per second, and it's going up. Why is it negative? Because I chose down as positive. If down is positive, anything up is negative. And then that goes for C as well. What did I say about the velocity of point C? I said that the velocity at point C is the same as that at point A with a different sign in the different direction. That means this will be a positive 4 meters per second all the way down. Ladies and gentlemen, this is a very important point. Very, 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 very important point. Please make sure that you understand what is going here. If you did not, rewind the video, try to listen to try to listen to that part attentively. Trust me when I say it is a very fundamental point to never forget. Cool. Right back to our symmetry once again. Just want us to speak about the final part on our hemisphere, right? So I'm going to take this hemisphere, shift it to the side, just like that. Right, another thing that I want us to discuss is what we call time symmetry. So when I say time symmetry, what do we know about something symmetrical? Remember, when we say something is symmetrical, we mean one side is the same as the other side, right? So when you speak about time symmetry, you are saying that the time for one side must be the same as that of the other side. Meaning, if I put my symmetrical line along the point B, right, what happens? I have my side, let's say X, and I have another side on the right-hand side, which is Y. What you must know is that side X is basically the same as side Y. And if that's the point, that means the time must also be the same. Meaning, the time it takes to move from A to B must be equal to the time it takes to move from B to C. So, for example, if from A to B it's 2 seconds, then from B to C it must also be 2 seconds. Once again, if the time from A to B is 0.2 seconds, then the time from B to C must also be 0.2 seconds. So if from A to B is 0.2 seconds, from B to C must also be 0.2 seconds. But now, what I want us to understand is that immediately when we move from A all the way to C, right? When we move from A all the way to C, that's the entire distance. What we need to do is take the time, these two times here, and add both of them. That is, it's going to be 0.2 plus 0.2, which becomes 0.4, right? So that is a very important point to understand. Mind you, the time will not always be 0.2. Please don't expect it to always be like that. This is just for illustration and explanation purposes. So it is very important that you understand how time symmetry works. From A to B, the time must be equal, from the time from A to B must be equal to the time from B to C. However, the time from A to C, I think it's best if I write it in a mathematical manner. I'm basically saying that the time from A to C is basically equal to the time from A to B, right? Plus the time from B to C. If A to B was 0.75 seconds, that means the time from B to C must also be 0.75 seconds because of time symmetry, right? However, from A to C, this will be 1.5 seconds. So that is what I needed you to understand right now. That is a very important point to understand, ladies and gentlemen. Very, very important. Please make sure that you understand that part. Right, so I'm going to erase this and I'm going to go back to my building diagram before I finish off this video. Cool. So let's see. Right, just trying to remove this. Right, so now we go back to our building, right? So I'm going to use that information that I created from my hemisphere in the very same diagram. Remember, I'm going to start by having my symmetrical line across B, right, like that. And I should know that the time it takes to move from A to B must be equal to the time it takes to move from B to C, right? And obviously, once again, the time it takes to move from A to C must be equal to the time it takes to move from A to B, right? Plus the time it takes to move from B to C, right? This is when we are talking about delta T in particular. No, man, it should be delta T according to time symmetry. Now, what do we know about A and C? Once again, right now, I'm just writing down all the things I need to know. Remember that at the point A, whatever the velocity of A is at point A, that means that the velocity at point C, okay, let me just write it in this way. Remember our portion here that we had in this point, that's what I'm going to write down, right? So whatever the velocity was, so the initial velocity at point A is equal to the final velocity at point C, right? Why am I having two equal signs? So the initial velocity of A must be equal to the final velocity at C. However, the velocity final at point C will, remember, will have the same magnitude as the one at A, right? It will have the same magnitude as the one at A in a different direction. Right, so it's going to be in a different direction with a different sign. Okay, so these are all the things that you must remember. Now, another thing that I want to mention real quickly before I end off this video is this. Now, pay careful attention here, ladies and gentlemen. It's very important. It's very important, this one. Yeah, it's very important. Okay. What I want you to understand is that at point D, one would assume, right? One would assume, make a very quick assumption that at point D, the velocity, let's say it's the final velocity, will be equal to 0. Please, ladies and gentlemen, that is not true. Do not assume that the final velocity at D is 0 unless the examiner says it is 0. How will the examiner tell you that it's 0? They might actually say, when the ball hits the ground, it comes to rest. That is the only time you can say the final velocity at the ground is 0. If that was not said, do not assume that the final velocity is 0. That is not true. Please, 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 do not make that common mistake that I've seen all the time. Instead, what you must know is that the velocity at D is a certain numerical value that you would obviously have to calculate for during a certain question that you are attempting to answer at that particular moment in time. Right. A very right. Hopefully that everything was very clear with you guys here. But before I end it off once again, I just want to mention, I'm not sure if you guys can see that I keep saying before I end off, because I always see that there are important things that I must make sure that you understand that you have, right? So I want you to know that if I am required to maybe calculate something of the motion of the ball, maybe let's say they say calculate the change in time, right? They say calculate the time it takes the ball to move from A to D. They won't say from A to D. Oh, by the way, these letters, these A, B, C, D, these letters will not be in the exam. These letters are not letters given to you by the examiner. I use these letters for myself and for you so that we can be able to understand our diagram, right? So it's very important to note that. Please don't expect to see letters in your diagrams in an exam. Right, so let's say they want you to calculate the time from A to D. That is the point from when the ball was thrown up until it hit the ground. That means you must consider the entire motion of the ball. That means you must consider the motion from A to B, from B to C, and from C to D. However, I want you to always remember, never forget to calculate the height above the roof to the maximum height. I want you to calculate, let's call this height 1, and we're going to calculate height 2. Please don't forget to calculate height 2. Height 2 is the height from the roof to the maximum height. What is height 1? The height 1 is the height from the ground to the roof of the building, right? And what is height 2? Height 2 is from the roof of the building to the maximum height, that being point B. Right? That's a very important thing to remember. And once again, I also want us to just think about our little friend here, our diagram here. What I want you guys to know is that when we are talking about this certain diagram in particular, so that would be, right? Check something. Very important point that I don't want to miss. So I'm just going to erase this height 2 thing, right? Remember, I've explained that. Hopefully it was understood. And I'm going to remove this point here. Now, ladies and gentlemen, I want you to listen to me very attentively. Once again, I'm going to bring my diagram a bit down so that I can have space to write at the top, because I need to write at the top at this point. Okay, that's a bit too down. Right there. Okay, there we go. So I want you to understand something, right? What I want you to understand is that, once again, I'm going to continue with my symmetrical line here. So I'm going to have two different sides. So I'm going to call this side here, we're going to call it side X, and we're going to call it side Y, right? So these two sides are separated by my symmetrical line. Now, what I want you to know is that, once again, at point A, that's where the initial velocity of the ball is, right? So we are looking at motion from A to B. That's side X. When we're focusing on side X, that's motion from A to B, right? So I'm going to try to write that down for you guys. So motion from A to B is side X, right? So check something. So now looking at side X, that's the motion from A to B. What I want you to know is that at that point, the initial velocity is an unknown value that you will be given in the exam, or you might be asked to calculate. But at point B, right, this is at point A. What do we know about point B? We know that at point B, we have our final velocity. And what did I say about the final velocity? Aha, because it's the maximum height, the final velocity is 0. So that is at point B. Right over here, I said it right there, right? Cool. Now I want you to focus very carefully. When I look at side Y, right? Notice side Y. Side Y is from B to C, right? We are focusing on the hemisphere initial. Okay, let's say side Y is basically from B to D, right? Side Y is from B to D. But I want you to focus on something. Now check something. With that being said, you'd notice that the initial velocity will be equal to 0, and that will be at point B. Now, journey with me. We are now focusing on side B. We are now focusing on side Y. We are going to disregard side X. So think of this picture. So I want you to take your hand as you're looking at the video and cover side X, right? Cover side X and focus only on side Y. You would notice that when you focus on side Y, you're starting at your starting point will be on point B. That is where the final velocity was 0. But now that we are starting at point B, it's going to be our initial velocity, our new initial velocity, and it's going to be 0. And once again, at point C, the final velocity becomes a negative value of what the velocity was at point A, right? So this is at point C, right? So notice something. At point C, right, the final velocity is equal to negative the velocity at A, right? I hope you guys can see that. And then obviously the velocity at D would be the final velocity at, well, the point D. We would have to calculate that. So these are very important things that I want you to understand. Once again, ladies and gentlemen, cover side Y. As you're watching this video, I need you to cover side Y and then look at the left side, right? So what do you notice? You start from A to B. At A, you have your initial velocity, and at B, you have your final, which is 0. You cover now side X. From side X, you are starting from B all the way to D. So what do you notice? You'd notice that your new starting point becomes point B. Therefore, your new initial velocity will be the velocity at point B. The velocity at point B is always 0. That is why the new initial velocity is going to be what? 0. And then you continue to point C. At point C, what did I say? I told you that at point C, the velocity is equal to the one at A, obviously with a different value, right? Cool. And then now, at point D, the velocity would then be unknown. It would be a value that you would have to calculate in an exam. Right, I really hope that was very clear to all of you guys here. So what's going to happen is that in the next video, we're going to be doing a couple of questions just so we can understand what goes on here. And then we can look at graph questions on VPM. And then after that, we do questions on graphs. And then we can then conclude this topic. But from me to you, I will see you guys in the next video. Goodbye.